Hello, linear algebra students. The topic of this video lesson is the inverse of a matrix. Now, a diagonal matrix is a square matrix where all entries not on the main diagonal are 0. An example of a diagonal matrix would be, I'll do a 3 by 3. So you can do anything you want on the main diagonal, including have a 0, but all the other entries must be 0. Now, an identity matrix, or also called a multiplicative identity matrix, is a diagonal matrix with 1s on the main diagonal, where I sub n represents the n by n identity matrix. So I sub 3 would be this square matrix, 1 down the main diagonal and 0s everywhere else. Compute the following products and generalize your findings. Okay, focusing on this first product, bring out the 1, 0 and place it on top of each column of the matrix on the left. Drop it onto the 6, 0, multiply corresponding entries, and add the results. So we get 6 plus 0 in this case. That gives me a 6. And then drop the 1, 0 onto the 5, negative 2. That's going to give me 5 plus 0, or just 5. And then we're done with the first column. And now we're going to grab the second column right here, the 0, 1, and drag it out. So we put the 0 and 1 up above. And now we drop this 0, 1 onto the entries. 0 plus 0 is what we're going to get the first calculation, which is 0. And then for the second calculation, we're going to get 0 plus negative 2, which is just negative 2. Now observe what happened here. We had a matrix A. We multiplied it by an identity matrix, I sub 2 specifically. And if the context is clear, you don't need to bother putting the subscript on the I. You can just say I. It's a 2 by 2 matrix here. And the result was the matrix A again. Let's try this again, but we multiply I on the left side. Now remember, matrix-matrix multiplication is not commutative, meaning in general, AB is not equal to BA. But let's see what happens if we switch this around and do I times A. So we're going to grab the 6, 5, write them up above, drop them onto these entries. We get 6 times 1 and 5 times 0, add those products, and we get 6. Now grab the 6, 5, drop it onto the 0, 1, multiply corresponding entries, add the results. We get 0 plus 5, we get 5. All right, then we do the same thing now. Grab the 0 and 2, bring them above the columns of the matrix on the left. We get 0 plus 0 initially here. And then we drop this 0, negative 2 down onto this row, and we get 0 plus negative 2. We get negative 2. And notice we got the same matrix A all over again. So what we're seeing here, if we multiply the matrix A by the identity matrix, we get the matrix A back. And it doesn't matter if we put the identity matrix on the right or on the left. Therefore, AB would be equal to BA in the case where one of those two matrices is an identity matrix. You can also see why this is called the identity matrix. It's because multiplying by this matrix doesn't change the other matrix. The next example, we do have a 3 by 2 times a 2 by 2, so the result should be a 3 by 2. Grab the 1, 0. Calculate, we get 1 times 1 plus 0 times 4, so we're just going to get, basically we're just going to get the first column when I do this, because the 0 on this right orange 0 is going to zero out all the entries in the second column. So, and the 1 will just preserve all the entries in the first column. So we are just going to get the first column when I multiply by the 1, 0. And now let's then multiply by the 0, 1 and observe what happens here. The left 0 will zero out the first column, and then the right 1 will just preserve the second column. So it's easy to see that when you multiply, in this case, that we wind up getting the same matrix again. And this was a case where we did a matrix B times a matrix I, and we got the matrix B again. Of course, the dimensions did have to make sense, right? So we had a 3 by 2. We had to multiply that by a 2 by 2 identity, right? I had to pick a 2 by 2 identity so that the interior numbers here matched. And we wound up getting B again. We get that 3 by 2 matrix back. In this case here, we have the identity matrix, size 3. So this is a 3 by 3 identity matrix times some matrix. This is the matrix B all over again. But this time, because we're putting the identity on the left, it has to be a 3 by 3 so that it can be multiplied by a 3 by 2, and that the result is going to be B all over again. And I'll leave it to you to verify that when you do this multiplication, we wind up getting the same matrix as B. So it didn't matter what side I put the identity matrix on. The size of the identity matrix did matter depending on what side of the matrix B we placed the identity. But in general, if you have a matrix A and you multiply it by an appropriately sized identity matrix, you will always get A. And if you have an appropriately sized identity matrix on the left and multiply by any matrix A, you will always get A still. Okay, let's go to the next page. Suppose the product of two square matrices A and B is the identity matrix. Then the two matrices are said to be multiplicative inverse matrices of each other, or we can simply say inverses of each other. And each matrix is called invertible or non-singular. Furthermore, we use the notation A raised to the minus 1 to represent the inverse of A. Now we're going to experiment here. We have two matrices that are going to be multiplied. Let's take that 2, -5 and write it up here above the columns of the matrix on the left. We got 2 times 3 is 6, 5 times -1 is, or -5 times 1 is -5, and 6 and -5 add to 1. Now drop that 2, -5 onto the next numbers. We'll get 10 minus 10, we'll get 0. Now take the -1, 3, bring them up here, and we have -1 times 3 and 3 times 1. So -3 plus 3 gives us 0. And then dropping onto the next row, we have -5 and +6 give me +1. So notice in this case, we got the identity matrix. So if we have a matrix A times a matrix B, and that produces the identity matrix, this is the case where we say that A and B are multiplicative inverse matrices of each other, or simply inverses. And we can say that, so if A times B is equal to the identity matrix, then we can say that B is the multiplicative inverse of A. So we write it's equal to A to the minus 1. So in general, we have the following statement. A times A inverse will always give you the identity matrix. And let's look at the product the other way around. So I'm going to switch A and B and multiply. Now normally A times B is not equal, or not guaranteed to be equal to B times A, because matrix multiplication is not commutative. But let's see what happens when I do flip them around in this case. So we have 3, 5. Let's bring that up here. 3, 5. 6 minus 5, we get a 1 in the first entry. And then we'll get -15 plus 15 for the next entry. We get 0. Now repeat with the 1, 2. 1 times 2 and 2 times -1. Add those products together, we get 0. And then we have -5 and 6 for the next one. -5 and 6 add to 1. And sure enough, we get the identity again. Now this is not a coincidence. So if A times B equals I, then we also know that B times A will also equal I. In other words, you can do A inverse times A and get I as well. It doesn't really matter on which side you put the inverse. They're inverses of each other, and the order of their multiplication does not matter. Of course, we could also say that A is the inverse of B, so we could also use this notation. Okay, now an elementary matrix is a matrix obtained by performing one and only one elementary row operation on an identity matrix. Produce the 2 by 2 elementary matrix for each indicated row operation. Okay, so what we're going to do is we're going to take the identity matrix, the 2 by 2 identity matrix, and we're going to do triple of row 1. And when I triple row 1, we get a new matrix. It's not equal, so make sure you don't put an equal sign, put an arrow. We get a new matrix that is 3, 0, and then the second row we didn't change. This is an elementary matrix, so we're going to call this E sub 1. Let's create a different elementary matrix. So you always go back to the identity. So in this case, we want to interchange rows 1 and 2. So this will lead to a new matrix. I'll use an arrow. That new matrix, the bottom row will be the first row, and the top row will now be the bottom row. And this is an elementary matrix. We'll call it E sub 2. And then our third case, let's do the third type of row operation, where we begin with the identity matrix, and we do the row operation indicated, -2 times row 1, add row 2, to produce a new row 2. And this leads to a new matrix. The first row we do not target for change, so don't change the first row. But then in our head, multiply first row by -2, add it to the second row, and get a new second row. 1 times -2 is -2, add to the 0, we get -2. And the -2 times 0 is 0, add to 1, we get 1. And then we're going to call this E sub 3. For the matrix A below, calculate the product EA. And make sure you go in this order, don't do AE. For each elementary matrix E above. Generalize your findings. All right, so we're going to do E1 times our matrix A. So let me rewrite E1 was 3, 0, 0, 1, and multiply that by the matrix A, 3, 1, 5, 2. 3, 1, 5, 2. Grab the first column of A, which is 3, 5, put that here, drop it down onto the rows, multiply corresponding entries, and add the results. And we're going to get a 9 plus 0, so just 9. And drop the 3, 5 on the 0, 1, we're going to get 5. Now let's take the second column of the matrix A, 1, 2, put it above the columns of E. We get 3 plus 0, we get 3, and then drop them down to the next row, we get 0 plus 2, or just 2. Now notice the result. Compare it to the matrix A. You'll notice that the first row of our result is 3 times the first row, which is exactly how we produced the elementary matrix, E1. So in other words, we should notice that just 3 times row 1 of matrix A also yields the same result. Now let's do E2 times A. Carry out the multiplication. We're going to get 0 plus 5, so we get 5 in the first one in the 1, 1 position, and then we get 3 plus 0, and we get 3 in the 2, 1 position. The 1, 2 position will give us a 0 plus 2, which is 2, and the 2, 2 position will give me 1 plus 0, which is 1. Notice that if I were to take the matrix A and do a row 1, row 2 interchange, that also yields this matrix. And doing a row 1, row 2 interchange is how we produced the matrix E2. Okay, now let's do E3 times the matrix A. Based on what we've been seeing with the other examples, I'm guessing what's going to result here is that the end result will be the same result should I simply do the same row operation on A that I did on the identity matrix to produce E3. So repeat this same row operation, but do that to A, and that should be the result of our multiplication here. So I'm going to get my answer by doing that row operation on the matrix A that you see right here. I'm going to -2 times row 1 and add it to row 2. Let's see what we get. Keep row 1 the same. -2 times row 1, looking at row 1 here, and add it to row 2. So we have -6 plus 5 is -1, and -2 plus 2 is going to give me 0. Now this should be the result, but let's go ahead and actually do the matrix multiplication. So this time I will show it again. We have the 3, 5, put that there, drop it down to the row. We have 3 plus 0 is 3, and drop it to the next row. We would have -6 plus 5, which is -1. So that confirms the first column of our result. And now let's take this 1, 2, do the same thing, multiply. We get 1 plus 0, which is 1, and then we get -2 plus 2, which is 0, and that confirms the second column of our result. So yes, doing this matrix multiplication with E3, where E3 is on the left, winds up effectively performing the row operation on A. That was the same row operation that we performed on I to produce E3 in the first place. So what we're seeing here is that all elementary row operations that you would ever want to perform on a matrix can be accomplished by multiplying that matrix by an appropriate elementary matrix on the left. Right? You got to put the E on the left and then the matrix A on the right. And then that matrix multiplication effectively performs the row operation that's desired. Let's go to the next slide. All row operations can be reversed, which suggests that every elementary matrix is invertible. Find the inverse of each elementary matrix below and confirm in each case that E inverse times E times A equals A. Now, we haven't really talked about how to find an inverse matrix yet, but it does make sense that if you were to take some matrix A and perform a row operation by multiplying it by E1, and then perform another row operation, so every time you do another row operation, the new E just goes on the left of the product. If you do another row operation, you would put that over here, and then do another row operation, put that one over here, etc. So you could just produce this chain of E's going off to the left here, where E1 is the first row operation, E2 is the second row operation, etc. And because matrix multiplication is associative, you don't need any of these parentheses. You can just write this, and you can do this multiplication basically in any order. So you can multiply all these together first, and then multiply that by A. There you have some options. But if you were to do a row operation and then simply reverse it to go back to A, that would suggest that there's a second row operation you can perform, and that the result here will wind up being A. This means that whatever this is, it has to be the identity, because the identity times A is the only way you can get A back. Which means that if E1 and E2 multiply to be the identity, that means that E2 has to be the inverse of E1. All right, so looking at this, here's our matrix A. Let's look at our E1, E2, E3. These are the same E1, E2, E3 that we had from the earlier slides. Let's begin by looking at this matrix. How was it obtained from the identity matrix? Well, you can clearly see that this was the result of tripling row 1, because row 1 used to have a 1 up there. So we can see that this matrix here, this elementary matrix, is associated with tripling row 1. E2. How did you get E2 from the identity matrix? We did it by interchanging row 1 and 2. And hopefully you can just recognize that by looking at the result. And then looking at E3, the identity matrix, what was done to the identity matrix, which row operation to produce E3, and you can just track where the non-zero entry is off the main diagonal and then use the pivot entry in that same column. So if we were to multiply column or row 1 by -2 and add that to row 2, that would produce this elementary matrix. So you want to be able to look at this matrix and deduce what the elementary row operation was. This was a -2 times row 1, then add that to row 2 to produce a new row 2. And here's our 3 types of row operations all represented. Now, how would you go about reversing these? Well, if you want to reverse tripling row 1, let's write down the reverse operation in orange. Then if you wanted to turn this back into a 1, you basically just need to do 1/3 times row 1. So if I do 1/3 of row 1, that will take me back to the original matrix. How do you reverse interchanging 2 rows? We just interchange them again. So in this case, you just do another row 1, row 2 interchange, and that will put right back the matrix right back to where it was. And then how do you reverse doing -1 or -2 times row 1, adding to row 2 to produce a new row 2? Well, you might just want to ask yourself how to use this matrix to make the -2 back into a 0. Well, you would do now +2 times row 1 and add that to row 2. And so the reverse row operation would be to do +2 times row 1, add that to row 2 to make a new row 2. Now we're going to create elementary matrices by using these orange row operations instead. The notation we're going to use is E sub 1 inverse. Now when you create an elementary matrix, always do it by beginning with the identity matrix. Imagine the identity matrix and then perform this orange row operation on it. So that means do 1/3 of row 1. So multiply the top row by 1/3, and that's going to give me a 1/3 0 and a 0 1. This should be the inverse matrix of E1. Let's do now the inverse matrix of E2. All right, so begin with the identity matrix and perform this orange row operation on it. In this case, that actually gives us the identical matrix that E2 was in the first place. So sometimes the matrix is its own inverse. And the last case, E3, inverse. So do the orange operation, but begin with the identity matrix. Double row 1 and add that to row 2 to make a new row 2. And so row 1 will not change, so 1, 0, still there. But when I do this row operation, double 1 add 0 is 2, and double 0 add to 1 is 1 still. Okay, now these are the 3 inverses of the 3 elementary matrices. Now let's confirm. For each of these pairings, we wanted to confirm that E inverse, that we're claiming is E inverse, times E times A equals A. So in this first case here, we have E1 inverse times E1 times A, and we want to confirm that this will give us A. Now you could do this in multiple ways. You could first do this multiplication and then finish out the product, or it'd be sufficient because of the associative property that you could just multiply these two first and then times A and see if you do in fact get A. I'm going to take this approach. If I do E1 inverse times E1, I'm expecting to get the identity matrix because that times A would guarantee to give me A still. So let's go ahead and rewrite what E1 inverse we said was 1/3 0 0 1 times E1, and E1 was 3 0 0 1, and then times the matrix A. We want to see that we get the matrix A. So grab that 3 0, bring it up here, drop on the corresponding entries. 3 times a third is 1, 0 times 0 is 0. Add those results, we get 1. Drop the 3 0 on the 0 1, we get 0 plus 0. And now let's focus on this 0 1. Drop them on the rows, we get 0 plus 0 is 0, and then we'll get 0 plus 1 is 1. And sure enough, we do get the identity matrix. This confirms that what we said about the claim that we made, that this matrix that we created right here, we sort of made a claim that that was the inverse matrix. Well, we just basically proved that is the inverse matrix, because when you multiply these two matrices, E1 and E1 inverse, you do get the identity. So that it is in fact the inverse. And then the rest of the multiplication I don't really need to do, because the identity times any matrix will not change it. So we'll just put a check mark. Let's do the same now for the other pairings. Let's try E2 inverse times E2 times A and see if we in fact do get A. And again, this will just mean I just need to prove that this is the identity matrix. So E2 inverse we said was 0, 1, 1, 0, and E2 was also the same one, 0, 1, 1, 0. All right, doing the multiplication, imagine that 0, 1 right here. Drop it onto the rows. We have 0 plus 1, so we get 1 for the first entry, and then 0 plus 0, We get 0 for the second entry in the first column. 1, 0, 1, 0. Drop it onto the columns. We get 0 plus 0 initially, and then we get 1 plus 0 for the second entry of the second column. And sure enough, that is the identity matrix. And the identity matrix times A, we won't bother doing that calculation again. Yes, we get A is equal to A, or identity times A is equal to A. Check. This works out. And let's verify for E3. So E3 times, or its inverse times E3 times the matrix A. Let's see if we do in fact get A. E3 inverse was 1, 0, 2, 1. And E3 was 1, 0, negative 2, 1 times the matrix A. We'll see if we get the matrix A. And doing this multiplication, the 1, negative 2, 1, negative 2, we get 1 plus 0, which is 1, and we get 2 minus 2, we get 0. Now grab the 0, 1, write them up here, 0, 1, drop them onto the rows, and we get 0 plus 0, and we get 0 plus 1. And sure enough, yes, we do get the identity again. And so we have the identity times the matrix A. That will, of course, give us the matrix A. So all the claims we made about these inverse matrices are true in the sense that they are, in fact, inverses. Okay, let's go to the next slide. Suppose A is a square matrix that is n by n. The following statements are equivalent. Now, when you say that statements are equivalent, it means that basically that if one of the statements is true, then all of them are true. And if one of them is false, all of them are false, which mathematically means that they all imply each other. So statement 1 implies statement 2, and somehow statement 2 should imply statement 1. And you could make this this double implication connecting any pairing of these 6 statements. Now, this class does not focus on rigorous analysis of claims made about matrices and linear algebra in general. This is a applications-focused class, so we won't be going into the weeds on proving that all of these imply each other, but I will do a few basic simple arguments that show how one leads to the other. But in the end, a rigorous analysis establishes that all 6 of these are equivalent statements. Let's begin just by saying, let's assume that statement 1 is true, that matrix A is invertible. That means it has an inverse. By the way, not every matrix is invertible. We'll talk more about that momentarily. If matrix A is invertible, now let's see if that somehow leads us to conclude what statement 2 is claiming. So let's start with what statement 2 has. We have a matrix A times a vector x is equal to a 0 vector. This would be a situation, right, where you have some sort of matrix like 1, 2, 3, 5, multiplied by some vector like xy, and is equal to the 0 vector, which in this case would translate into this system of equations. X plus 2y has to be 0, 3x plus 5y has to be 0. So basically solving this system, and we are simply writing that system in matrix form, this form right here. If we have a system in matrix form, ax equals 0, and A is invertible, then we can multiply both sides of this equation on the left by the inverse of that matrix A, right? So whatever the inverse is, we know it has one because we're assuming statement 1's true. We're assuming that A is invertible. We have some sort of n by n matrix, and we're multiplying it by the n by 1 0 vector. And just to illustrate, if you have any matrix, doesn't matter, and you multiply it by an appropriate size 0 vector, when you take that 0, 0 and bring them up here and drop them on the rows, multiply and add results, you're going to get the 0 vector back. You're going to get 0, 0 as a vector. So similar to multiplication of scalars by 0, like 5 times 0 is 0. Well, matrix times an appropriate 0 vector, or even a 0 matrix, will just give you a 0 matrix back. Now keep in mind the dimensions here. We're assuming A was n by n. X we'll assume is n by 1. And when you multiply these together, you will get the inner numbers match, so the outer numbers, you'll get an n by 1 0 vector. So A inverse, if it exists, is also n by n. So we have an n by n inverse, multiplying it by an n by 1 0 vector. This will just give you another n by 1 0 vector. Now on the left, we have the identity matrix. When you multiply A inverse and A times this vector x, remember vectors are also matrices. And we have A inverse times the 0 vector, which will just give you the 0 vector back. And the identity times anything doesn't change it. And so we just get vector x equals 0. In other words, if A times x has to be equal to 0 and A is invertible, then the only solution is that x has to be 0. So back in that context of an equation, remember we had something like x plus y equals 1, or 3x plus 5y equals, sorry, not 1, these are both zeros. If you have a system and the coefficient matrix is invertible, what it's saying is that the only solution in the system is if x is 0 and y is 0. Okay, statement 3 says that the system ax equals b is always consistent and has the unique solution x equals a inverse b. So this is a pretty similar approach. If if we know that we have a system that's written as ax equals b, now b is not necessarily the 0 vector, so that'd be like taking our system that we had, I'm just making these up as I go. Instead of having zeros on this side, you could have anything you want, something like this. And the claim here is that ax, if a is invertible, if the matrix A is invertible, then you simply multiply both sides by its inverse. And make sure you put the inverse on the left of each side. Here we get the identity times the vector x, which will just give you the vector x. And the other side, we have to do a calculation. I don't know what this is going to be. It depends on what the vector b is. But the inverse times b will effectively be our solution to the system. It'll be our unique solution. It doesn't matter what b is. B can be any vector. If b happens to be the 0 vector, then we have statement 2 again. By the way, some terminology. A system written this way, where the vector on the right is a 0 vector, is said to be homogeneous. We'll talk about this later in the semester. And this system down here that has a non-zero vector on the right, assuming b is a non-zero vector, right? If b is not the 0 vector, then we say that it's inhomogeneous. Some terms that we'll be using later in the semester. Not super important right now. All right, let's look at statement 4. The matrix A must reduce to the identity matrix. Well, this one is a consequence of our statement right here. So if we take this fact and we make an augmented matrix out of this, we would have the coefficient matrix A and then that 0 vector as the last column, right? We create an augmented matrix. And because the solution is going to be all the variables in the equation have to be 0, this should boil down to basically the identity matrix on the left, and still maintain a 0 here. Because this is what the matrix, the augmented matrix, should look like if you're going to make the claim that there's a unique solution and all the variables have to be 0, right? So, for example, in the case of a 2 by 2, let's just do a 2 by 2. This would be your augmented result. Convert this back to an equation, it would read x equals 0, y equals 0. And if this was a 3 by 3, right, then this should be the result of your augmented matrix, suggesting that x, y, and z all have to be 0. Well, anyway, any dimension it is, the matrix A, when you do enough appropriate row operations, should become the matrix I, so that we can make the claim that all the variables have to be 0. All right, so the matrix A reduces to the identity matrix. In other words, the identity matrix is the reduced row echelon form of the matrix A. Number 5 is that the matrix A is a product of elementary matrices. Well, this makes sense because there are enough row operations. You can do some sort of series of row operations on A to reduce it to I. So that means that if you were to start with the matrix A and do a row operation, and then do a second row operation, etc., and do enough of them, we'll say k of them, that this should just become I. What we're going to do is we're going to basically solve this equation for A. And I'm going to do this by one removing the identity, or the elementary matrices from the left side of this product. For example, if I take this statement and I multiply both sides on the left by the inverse of the furthest left elementary matrix, which would be EK. And then I use the associative property and just multiply these two together first. Those will cancel and become the identity matrix. Let's pretend we do this just so I can get rid of some numbers. Let's pretend that we do this in 5 steps. So in other words, the very last elementary matrix is E5. And maybe it takes 20 row operations, but it doesn't matter. It takes some certain number of row operations, and let's reverse them one at a time. So the very next line, E5 inverse times E5 gives you the identity, and the identity times the rest, you don't need to bother writing the identity. So our statement boils down to just E4, E3, E2, E1, A equals, and then E5 inverse times the identity is just E5 inverse. So one by one, I'm going to shift these elementary matrices from the left side of the equation to the right side. So I'm going to multiply both sides of this new equation on the left by the inverse of E4. Now we're going to get the E4s right here are going to cancel and become I, so they'll just disappear from our statement. So we're just down to E3, E2, E1, A equals E4 inverse, E5 inverse, etc. And we can keep this up until we finally get A isolated. Every elementary matrix has an inverse, so this is completely possible. So we get A is in the end going to be equal to E1 inverse, E2 inverse, etc., up to E5 inverse. And the product of these all of these are also elementary matrices, right? The inverse of an elementary matrix is another elementary matrix. And so we see now that A can be solved for, if you will, and A is a product of elementary matrices. Okay, and then number 6, the rank of the matrix A is n. That one's an obvious conclusion from statement 4, But statement 4 says that the matrix A reduces to the identity matrix, and then the rank is simply you count all the pivot positions. So there will be n pivot positions, so the rank will have to be n. All right, I think that's enough discussion on this. Again, I'm not looking for a rigorous analysis here to prove the double implications between all of these statements. And we're going to move forward taking for granted that all 6 of these statements are either all true together or they're all false together. In other words, they're all equivalent. Okay, now if it exists, we're finally to the point now that we want to discuss how to find an inverse matrix. And we're going to devise a strategy. But before we do that, let me go up here and take a look at one of these statements that's going to be important for our strategy. And that is the fact that if you start with the matrix A, if it's invertible, it can reduce to the matrix I by doing enough row operations. And I don't know how many it will take. We'll say E1 through EK. But E1 through EK times the matrix A should give me the identity. Now, if A is invertible, what I'm going to do this time is I'm going to multiply both sides of this equation on the right by the inverse of A. And then use the associative property that I can do A times A inverse and just get the identity right there. And so basically what this is saying is that EK through E1 times the identity will be equal to, and then on the right side of the equation we have the identity times the inverse. Well, the identity times anything doesn't change it. This equals the inverse. Okay, now keep in mind what we started with. Let me get rid of all the red. We can see from this statement that if I start with the matrix A and do a bunch of row operations, that will produce the identity matrix. If I do those same row operations but to the identity matrix, that will produce the inverse of A. It's this reasoning that allows us to construct the following method for finding an inverse. All right, so this page, if it exists, the inverse of the square matrix A is found by row reducing an augmented matrix. This is A put next to the same size identity matrix. You row reduce it until you get the identity matrix on the left, so right there, and then whatever happens to the right side of this augmented matrix will reveal what the inverse matrix is. So let's do this for our first matrix A here. You begin by writing 3, 1, 5, 2, do a vertical line, and augment it with the same size identity matrix. Then basically all you do is you take this is now a 2 by 4 augmented matrix. You put it in a reduced row echelon form with the goal of getting the identity on this side. If A is invertible, this will be possible. If A is not invertible, this will not be possible. All right, well, let's begin. Okay, now the way I'm going to do this, I'm going to choose to multiply the top row by a 1/3 because I want to get a 1 right here, even though that's going to cause some fractions. Now, again, this is not the only way that you might go about doing this. There's a variety of strategies you could take. But let's just do 1/3 times the top row. So we get a 1, a 1/3, a 1/3, a 0. And then the bottom row we're not changing yet. Okay, so I got a 1 in my pivot position, and I want to get a 0 beneath it. So I'm going to do next -5 times row 1 and add that to row 2 in order to make this entry right there a 0. So this will give me the same row 1. That's not changing. But we will have a new row 2. -5, and make sure you do your row operation, to the entire augmented matrix. Don't just do it to this side only, but do it to these entries as well. So it's going to be 4 calculations we're doing here. -5 times 1 is -5. Add to 5 makes a 0. That's what I wanted. -5 times a third is -5/3. Add that to 2. Well, 2 is 6/3, and 6/3 minus 5/3 is 1/3. -5 times a third is -5/3. Add to 0, so -5/3. And -5 times 0 is 0. Add to 1, it stays 1. Okay, my next goal is to make this entry here a 1. I'm going to do this pretty easily by just tripling the bottom row. All right, so this does not change the top row. We have 1, 1/3, 1/3, 0. And now triple the bottom row. So it gives me a 1, a -5, and a 3. Okay, my next goal is to make this entry right here a 0. And then I'll have the identity matrix on the left. I'm going to multiply the bottom row temporarily by -1/3, and then add that to the first row to change the first row. So I'm not changing the bottom row. -1/3 times 0 is 0. Add to 1 stays 1. -1/3 times 1 is -1/3. Add to a third goes to 0. -1/3 times 5, -5 will be 5/3, and add that to 1/3 is 6/3, but 6/3 is just 2. So we get a nice clean number there. And -1/3 times 3 is -1. Add to 0 is -1. Okay, so we've gotten to the point now where we have the identity matrix on the left, and then on the right here, therefore, must be the inverse of the matrix A. So we conclude that A is invertible, and it has inverse of 2, -1, -5, 3. Now this should not be surprising. This matrix A was a matrix we've been looking at other slides. In fact, let me back up several slides. Matrix A was this matrix, and we have already knew what its inverse was because I gave it to you up front. 2, -1, -5, 3. Okay, let's try the matrix B. Do the same thing. Write down the matrix B next and augment that with the identity matrix of the same size, and then now do row operations to put this in reduced row echelon form, and hopefully we get the identity matrix here on the left. My first goal is to get a 1 right here, so I'm going to just multiply the top row by half. And then the bottom row we are not changing. Okay, my next goal is to make this 6 a 0, so we're going to multiply the top row by -6 temporarily, but add that result to the second row to change the second row. And now we'll do this row operation. -6 times 1, add to 6, will give us a 0. -6 times -1/2 will be 3. Add to -3 will also give me 0. -6 times 1/2 is -3. Add to 0 is -3. And -6 times 0, add to 1 will be 1. Okay, right here we can basically stop. We have a problem. This bottom row, I was not able to successfully get a 1 in this position, or non-zero entry in that position. If that position had been a non-zero number, then I would have been able to turn it into a 1 by scaling it. But when it's a 0, it means that our next pivot position is actually going to be to the right of our division line here. This is going to be the next pivot position. So it's basically impossible to make the left side the identity, because we would need to have a pivot. We would need a pivot position right here in order to do that. So we say B is not invertible. B has no inverse. B inverse does not exist. We can say, therefore, that means B is not invertible. And another way to say that a matrix is not invertible is to say that it is singular. A singular matrix is a matrix that has no inverse. All right, tying this back to our last page, when I tried to reduce B to reduced row echelon form, if you only focus on this left side, you'll notice it cannot reduce to the identity matrix. It's going to reduce to something else if you're just row reducing B and B alone. So B does not reduce to the identity matrix. So when you look at these statements, if any one of them is false, they're all false. So this statement right here, if a matrix does not reduce to the identity matrix, then all of these statements are false, including the top one. So we would say B is not invertible. In other words, you can say it's singular. Also, if you row reduce B and only B, you would have, this is the reduced row echelon form of the matrix B that we're looking at right there. Notice it has 1 pivot position, so the rank of B would just be 1. Well, that's not 2. B is a 2 by 2 matrix. So looking back up here, if we're working with a 2 by 2 matrix, and the rank of if that matrix is not the size of the number of rows or number of columns, it's not n, it's not 2. If it's not that number, so if statement 6 is false, then all of this is false. We know that the matrix has no inverse. It's singular. All right, so this collection of statements is very powerful. If you can prove one of them is false, you can conclude that all of them are false. And if you can prove that any one of them is true, you can conclude that all of them are true. And now let's look at matrix C, a 3 by 3. And then try to put this in reduced row echelon form in such a way that we see I3 over here. We're trying to get I3 on that side. If we can, then C is invertible. If we can't, then it's not invertible. All right, the first thing, row operation, I think it's pretty easy to do. I do see a 1 already in the second row. I'm just going to do a row interchange, get that up there into the first row. So let's just do that row interchange. Row, put it there instead, and then move both these back down. Next thing I want to change is I want this location here to be 0 and this to be 0, where the bottom one's already 0. So I just need that 2 to be a 0, and we're going to do the third row operation of multiplying row 1 by -2 and adding it to row 2. So -2 times 1 add to 2 is 0. -2 times 0 add to -2 is still -2. -2 times 1 add to 0 is -2. And -2 times 0 add to 1 is 1. -2 times 1 add to 0 is -2. And -2 times 0 add to 0 is 0. Okay, my next goal is to make this location a 1, but notice there's a 1 directly below it. So I'm going to just do another row interchange in this case. Okay, my next goal is to make this here be a 0, and also above a 0. Above is already a 0, so I just really have to worry now about that -2. And I'm going to multiply row 2 by 2 and add it to row 3. And we have 2 times 0 add to 0, 2 times 1 add to -2. 2 times 2 add to -2, that's going to be 4 minus 2, that's 2. 2 times 0 add to 1. 2 2 times 0 add to negative 2, and 2 times 1 add to 0. All right, next I want this position here to be a 1, so I'm going to just multiply the bottom row by a half. Okay, so the first two rows are not going to change. Make sure you copy those correctly. Third row will be 1/2 of what it was, so 0, 0, 1, 1/2, negative 1, 1. All right, my next goal is to make both of these entries here 0 using the pivot one that's just below it. So I'm going to do both of these at the same time. I'm going to do negative 2 times row 3 and add that to row 2, and then negative 1 times row 3 and add that to row 1. New second row, negative 2 times 0 add to 0 is 0. Negative 2 times 0 add to 1. Negative 2 times 1 add to 2 makes 0. Negative 2 times 1/2 is negative 1. Add to 0 is negative 1. Negative 2 times negative 1 is 2. Add to 0 is 2. Negative 2 times 1 is negative 2. Add to 1 is negative 1. Now let's make a new first row. Negative 1 times 0 add to 1 is 1 still. Negative 1 times 0 add to 0. Negative 1 times 1 add to 1 makes a 0. Negative 1 times 1/2 is negative 1/2. Add to 0 is negative 1/2. Negative 1 times negative 1 is 1. Add to 1 makes 2. And negative 1 times 1 is negative 1. Add to 0 is negative 1. And sure enough, we have the identity matrix, the 3 by 3 identity matrix on the left, which tells me that the inverse matrix of C is this 3 by 3 right here. Now, I encourage you to also be able to confirm these answers using technology. So I'm using the Desmos matrix calculator, and I typed in C and then new matrix, and then I increased the rows and columns so that we had a 3 by 3, and I made sure all the entries were correct. And I hit enter, and there's our C matrix. And then if I want to find the inverse of this, just hit C again, and then hit the A inverse sign, the A to the negative 1, and it gives us the inverse. And then you can show fractions or decimals. Now suppose A and B have equal dimensions and are each invertible. Also, the matrix D is diagonal, so that's just referring to this last entry here. That's going to be a diagonal matrix. Complete each unfinished statement and give examples where appropriate. Okay, so some properties relating to inverses. First of all, if a matrix A is square and it has an inverse, then its inverse is unique. It can't have multiple, different matrices that are both its inverse. This next statement, if you do the inverse of the inverse, that just gets you right back to the original. If you're to find the inverse of a product, now we're assuming A and B are both invertible, and to multiply them, therefore, they'd have to be both square and both be the same size. So A and B are both square and both the same size, and they're both invertible. And if you multiply them, it turns out that their product is also invertible, and that the inverse of the product can be found by doing the product of the inverses, but in reverse order. Let's verify why that's the case. So AB times B inverse A inverse, let's see what this would become. Well, because of the associative property of multiplication, I can multiply these two interior matrices together first, and B times B inverse is the identity. So this gives me AIA. The identity times anything doesn't change it, so I'll multiply A times I and just get A. And now I have A times its inverse, so in the end I get I. This matrix times this matrix gives the identity. So they must be inverses of each other. So the inverse of a product is the product of the inverses in reverse order, as long as all the A's and B's are all invertible. All right, the inverse of a scalar times a matrix A. This one's going to be equal to the reciprocal of that scalar times the inverse of the matrix A. Let's see why that's the case. If I take Ka and I multiply that by 1 over Ka inverse, right? The K and the 1 over K are scalars, so you can reorder them. You can multiply them together first, and K times 1 over K gives you 1, times A and A inverse. Well, multiplying by 1 doesn't change anything, so it's just A times A inverse, which gives you back to the identity matrix. So yes, it's true that Ka times 1 over Ka inverse will wind up just becoming the identity. So they are inverses of each other. If you have A to the n, so power, and you want to do the inverse of this, well, it turns out that you can just do the nth power of the inverse of A. I hope that makes sense, because if n were like, let's say n is 3, it's cubed. So if you have A cubed, and you multiply that by A inverse cubed, well, A cubed is just A times A times A, and A inverse cubed is A inverse times A inverse times A inverse. And now you can just start doing the associative property, multiply these two interior ones first and get the identity, so they go away. Then next I would multiply these two, that becomes the identity, they go away, and then finally, right, you can multiply by the these two, and that they will also cancel each other and become the identity. So in the end, this all just becomes the identity matrix. So the inverse of a power is the power of the inverse. A transpose. Now A has to be square if it's invertible, so A transpose will also be square and be the same size. And if A is an invertible, it turns out A transpose is also invertible. The inverse of the transpose is the transpose of the inverse. So basically you can interchange these two operations. Maybe we could do one quick example of that one. Let's go back to our 2 by 2 matrix A that we found the inverse, this matrix right here. So let's say A is 3, 1, 5, 2. And we've already shown that its inverse is 2, negative 1, negative 5, 3. All right, so the transpose of this matrix, turn the row into a column. So it'd be 3, 1, and then the second row into the second column, 5, 2. Well, according to what we're saying is that if I define the inverse of the transpose, I simply need to do the transpose of the inverse. So just do the transpose of this matrix here. So the first column will be 2 minus 1, second column will be minus 5, 3. And the claim is that these two matrices are inverses of each other. So this matrix and this matrix are inverses. We can prove that by simply multiplying them to see if they produce the identity. I'll do the 2, negative 1 first. We get 6 minus 5, we get 1. And then we get 2 minus 2 is 0. And then negative 5 times 3, and 5 times 3 are negative 15, and 15 add to 0. And then negative 5 times 1, negative 5 plus 6 gives me a 1. So sure enough, yes, they get the identity. And we have that the inverse of the transpose is the same thing as the transpose of the inverse. And the last one I want to talk about here is this diagonal matrix. So a diagonal matrix has the main diagonal can be whatever, but the non-main diagonal has to be 0. So let's just do a quick example of like a 3 by 3. Let's say we have the D11 position, the D22 position, and the D33 position, and zeros everywhere else. If all these diagonal entries, if dii are non-zero, then D inverse exists. And its inverse is the same diagonal matrix, but you invert all the diagonal entries. So it'd be 1 over D11, 1 over D22, and 1 over D33. And all the other entries are 0. So we'll just say invert the dii's provided, if the dii's are not 0. They have to all be non-zero. If any one of them is 0, then we would say that D is not invertible. So an example of an invertible, a diagonal matrix that is invertible, just make sure that you put, I'll do non-zero entries on the main diagonal. You can throw some fractions in there too. If this is the case, then we would have that its inverse. Just invert all of these. So 1 over 1 is still 1. 1 over 1/2, just invert the fraction, becomes 2. And then negative 1/3. And all other entries still 0. That's how you invert a diagonal matrix. And I will leave it to you to verify that this, in fact, when you multiply them, you do produce the identity matrix. Let's see if all dii is not 0. Let's go to the next page. If possible, solve each system below using the inverse of the coefficient matrix. All right, so let's take a look at this system here. We have u's and v's as our variables, and they're already in the same order, so let's just keep that order. Let's convert this to a matrix form. So the coefficient matrix would be 3, 1, 5, 2. We would multiply that by the variable vector of uv, and this equal the vector of constants, so 0, 0. So this is an ax equals 0 vector situation. And if you recall, we said that this was homogeneous. Now we know that the matrix A is invertible. We've already found it. This is the same 3, 1, 5, 2 that we've been working with. And so to solve the system, you simply multiply both sides by that inverse. Make sure you put the inverse on the left side of each side. The inverse times times A will become the identity matrix, and the identity matrix times x will just give us the x vector. So all we have to do is do the inverse times the 0 vector. And we've said that the inverse was 2, negative 1, negative 5, 3. That was the inverse. But when I multiply this matrix times the 0 vector, I'm going to get the 0 vector back. So both u and v have to each be 0. This is our only solution. Now, keep in mind that this coefficient matrix A right here was invertible. So if we go back to our 6 statements, right? So statement 1 is true. The coefficient matrix is invertible. Therefore, statement 2, the system AX equals 0 has only the trivial solution vector x equals 0. This is just what we confirmed. U and V both have to be 0. Okay, let's take a look at this one here. This time we have x, y's, and z's. So we have a 3 by 3 system. We have 3 variables, 3 equations. Coefficient matrix will be squared. So here's our coefficient matrix. Multiply that by the variable vector of x, y, z variables. And this should be equal to the vector of constants. Now be mindful of this minus 3. Add that to the other side. And our vector of constants would be 1, 4, 3. So this does have the structure. A times some vector x equals some vector b this time. And it's non-zero vector on the right. Remember our terms here. The system on the left, we called this system here, we called it homogeneous. And this system right here, we're going to call inhomogeneous because we have a non-zero, it's equal to a non-zero vector. Okay, but the matrix A, this is the same 3 by 3 that we found the inverse earlier. You'll notice it's the same matrix C. So I'm going to borrow the work that we've already done. Basically solve this equation for x by multiplying both sides by the inverse matrix. So we're going to do A inverse times AX equals A inverse times the vector B. And on this side, the A inverse times A becomes the identity matrix, and the identity matrix times X just becomes the vector X. And then, so all we have to do is do this calculation over here, which is exactly what statement 3 is saying right in our equivalency theorem over here. We have an invertible matrix, yes, and therefore this system AX equals B will always be consistent, and it's going to have this unique solution, the inverse of the coefficient matrix times the vector B. So we're just doing that calculation now to get our answer. And then, of course, borrowing the work we had before, vector x equals, let's go ahead and paste. So this was the inverse of this coefficient matrix that we had found earlier. We're going to multiply that by the vector B, so multiply by 1, 4, 3. And now we just have to do matrix vector multiplication to get our answer. So our answer will be, we take the 1, 4, 3, write them here, here, and here, multiply. So we have 4 times 2 is 8, 3 times negative 1 is negative 3, so 8 minus 3 is 5, and then minus a half. 5 minus a half is 9 halves. So we get 9 halves for the first entry. Now drop the 1, 4, 3 on the next row. So we get negative 1 plus 8 is 7, 7 minus 3 is 4. And now drop the 1, 4, 3 on the last row. I'll do the non-fraction calculations first. We have negative 8 plus 3. Sorry, negative 4 plus 3 is negative 1. Negative 1 plus a half is negative a half. Here is my solution to the system. X has to be 9 halves, Y has to be 4, and Z has to be negative 1 half. Of course, this would be easy to check that it works out. Just plug these numbers back into the system and see that, in fact, you do get true statements. Okay, and let's go now to our final page. Find conditions on each constant vector so that each system is consistent. Well, here in this case, the coefficient matrix is the same 2 by 2 matrix we've been analyzing. So we're trying to say what has to be true about the vector B so that this system is consistent. Well, because A inverse exists, we can go to our equivalence theorem. And because statement 1 is true, we know statement 3 will be true. In other words, that AX equals B is always consistent. Doesn't matter what B is. And it'll have a unique solution, A inverse times B. So down here, because the coefficient matrix A is invertible, we get to conclude that this is always consistent no matter what B is. Let's look at the other one. This matrix here, this was a matrix we had also already analyzed. If we go back, when we tried to find inverses, this was the middle one. The same matrix we see here, matrix B. And when we tried to find the inverse, we concluded that it had no inverse. So B is not invertible, which means that it's not true that AX equals B is always consistent. There could be some choice of B that is going to be problematic. And so this is where we want to come up with the conditions. What conditions must be true about the vector B so that this is consistent? Well, in order to do this, we're going to rewrite B as a vector. That would be, we'll say B1, B2 are its two components, its two entries. This matrix here has no inverse, so I can't multiply both sides by the inverse of the coefficient matrix to isolate the X vector. So I can't take that approach. But what I can do is write this as an augmented matrix. Not matrix form, mind you, but augmented matrix. And now I'll start to perform row operations so that we put this in reduced row echelon form. So I'm going to begin by doing, I'm going to say minus 3 times the first row, add that to the second row. That's to get a 0 where that 6 is. And then after that, I'm going to, in the same step, I'm going to cut the top row in half after it. So I'm actually doing 2 row operations at once. Well, I'm doing one at a time, but in the same step. So negative 3 times 2, add to 6 makes a 0. Negative 3 times negative 1 is 3, add to negative 3 makes a 0. Negative 3 times b1, add to b2. So let me give myself a little bit more space here. Negative 3 times b1, add to b2. So that's going to be my new entry right here. Negative 3 times b1, add to b2. And then I'm going to multiply the top row by a half. So you have a 1, a negative 1/2, and a 1/2 b1. Okay, now right now, this is technically is not in a reduced row echelon form, because in order for this to be in a reduced row echelon form, we would want this to be a 1 as well. But what we can certainly see is that the coefficient matrix is in reduced row echelon form, and we have potential for an inconsistent system, right? This down here is potentially problematic, right? Pretend like that we had a 3 right here in that bottom position. Then we would have 0 plus 0 equals 3, and we'd have inconsistent. So as long as, if this entry down here at the bottom is non-zero, then this is inconsistent. So we can say the following: inconsistent if negative 3b1 plus b2 is not 0. Consistent only if negative 3b1 plus b2 is 0. And so this tells me that there's an implied relationship between b1 and b2. And I could add the b1 to the other side, so that we could say that b2 has to be equal to 3b1. So we could say if the second entry of b is the triple of the first entry in b, then the system is consistent. And that's our condition. That's only for such b vectors where that's true, that we'll have a consistent system. And that's because the coefficient matrix was not invertible. Now, if the coefficient matrix is invertible, we're back over in this case, and in which case it doesn't really matter what choice. There are no conditions on b. B can be any vector you want, and you'll have a solution. Okay, that wraps up our lesson on the inverse of a matrix.